Our first topic is demand forecasting. We'll first take a look at three universal laws that describe the properties of demand forecasts. And here are the three laws of forecasting. The forecast is always wrong. The shorter the forecast horizon, the more accurate the forecast. And aggregate forecasts are more accurate than individual forecasts. For more information, you could take a look at these pages of this book. The first law is that the forecast is always wrong. This states that it is very difficult or impossible to predict the demand exactly. For example, I generated about 100 replications or 100 realizations of normal demand with mean 100 and standard deviation of 30. And what we notice when we plot a histogram is that the demand is almost always never equal to 100 exactly. So although on average it's 100, it's often bigger or smaller or sometimes quite far away. So you can almost never exactly predict the demand beforehand. And we also experienced in the news vendor model or the news vendor game that it is costly to ignore demand variability. So here's an artificial example I made up with some numbers. You don't actually need to know how to calculate all of these values. It's just to illustrate the point that it is costly to ignore demand variability. Suppose you look at a bakery which sells donuts, and we'll just assume these parameters to make things simple. So the cost is $8 and the price is $10 and the salvage is $0. You can calculate that the critical fractile in this case is actually 20%. So if you go through the calculations, the optimal order quantity is actually 75. If you just ordered the mean, you would get an expected profit of $80, but if you calculated the optimal order quantity and used that instead, your expected profit would be 115, which is more than 40% more than ordering using the mean. So this example illustrates how using the news vendor model can help you to take into account demand variability correctly. And it's definitely a lot better than just ordering the mean quantity and ignoring the demand variability. The second law states that a shorter forecast horizon gives you a better forecast. So let's look at an example. Is it easier to predict the weather tomorrow or the weather in 6 months? Obviously, it's much easier to predict the weather tomorrow because we have a lot more information about how the clouds are looking, how the winds are blowing, will there be a tropical storm, and so on. So we have a lot more information if we're trying to make a prediction in the short term. But trying to make a prediction in the long term is much more difficult because there's a lot of uncertainty. And the long-term forecast will be much more noisy or have much larger variability. As an example, let's look at the fast fashion retailer Zara, which benefits from understanding this second law of forecasting. So Zara is widely known in the industry to have very short production lead times. That means the time from when they design a fashion item to produce it to actually sell it in the store is very short, around 5 weeks compared to competitors such as H&M. Because Zara has such a short production lead time, they can have much better demand forecasts. Since they're only predicting the fashion tastes 5 weeks in advance instead of, say, 6 months. The third law states that aggregate forecasts are more accurate than disaggregate forecasts. So there are many different ways to aggregate the items for which you're forecasting. For example, you can be grouping across products, you can be grouping across time, you can be grouping across locations, and so on. Let's look at a very simple example. Is it easier to predict the demand of sales of blue iPhone XRs with 64 gigabytes of storage? Or is it easier to predict the sales of all colors and all storage levels of iPhone XRs? What do you think? So the reason that it's much easier to predict the sales of all colors and all storage levels is because there's randomness in what customers demand, but if there's high demand for one particular version, it will usually be cancelled out by low demand for another version. So that's why aggregate demand tends to be more predictable than disaggregate demands. I have an example to illustrate this, but let's first again take a short detour to talk about a little bit of statistics. So in statistics, there's something called the coefficient of variation. So the standard deviation quantifies how much variation or dispersion there is in a random variable or a set of data values. The coefficient of variation is basically the same thing as the standard deviation, but scaled relative to the mean. So one way to think about it is the standard deviation measures the absolute variability in something. For example, the demand is 500 plus or minus 100. So this tells you roughly how much variance there is in the demand. The coefficient of variation, however, is a percentage because it measures the relative variability. So the demand is 500 plus or minus 20%. In this case, the coefficient of variation is 20%. Here's an example of individual demand versus aggregate demand. Let's say we have one store, mean demand is 10, and this is the standard deviation. The coefficient of variation is about 32%. If you sum up the demand, the same demand, over 50 identical stores, so the stores have the same distribution, but not exactly the same demand. So it means store number 1 may have 10, store number 2 may have 15, and so on, but the distribution looks the same, all right? So if you sum up the demands over 50 stores, the mean demand is 500, the standard deviation is 22, which means the coefficient of variation is only about 4%. And just looking at the distribution shows you very clearly that there's much less variability in the aggregate demand. Another disclaimer, these calculations are only for illustrative purposes. Don't worry about how to calculate these things, all right? And let's look at how Apple benefits from understanding this third law of forecasting. So in 2018, Apple announced 3 phones, and they're different colors for the phones. They also have different storage sizes, so 64 gigabytes, 128 gigabytes, and so on. It's actually quite difficult to predict the demand for a particular model color storage combination. However, all of these phones actually use the same system on a chip, which you can think of it as basically the processor in the phone. So because of that, it's much easier to predict the aggregate demand for the chip because all the phones use the same chip. So the demand for this chip is basically the sum of the demand over all models, colors, and storages. In the second part of this topic, we'll be looking at forecasting methods. There are 2 types of forecasting methods, qualitative and quantitative. Qualitative methods rely on qualities, whereas quantitative methods rely on quantities, or measured numbers, basically. And qualitative methods rely on the judgments of so-called experts, whereas quantitative methods rely on statistical models. Qualitative methods are a bit more flexible because you can apply them even when you don't have measured numbers or historical data. But quantitative methods really do depend on having these past experience and past numbers. Qualitative forecasts tend to be a bit subjective and inconsistent, whereas quantitative forecasts are more objective and are reproducible. So if you have the same numbers, you run the same method, using the computer, it will give you the same answer every time. So the first qualitative forecasting method is personal insight. Basically, a single person, will use his or her past experience to try to make a forecast. The problem is it's highly subjective. It depends on who is the expert or the single person making that forecast. So all of you have heard about coronavirus, I imagine. Donald Trump gave a particular forecast about how COVID would be like in the US. Anthony Fauci gave a different forecast. So this shows you how the forecasts can be very subjective. And this method works well if you find a true expert to make the forecast. If you find an idiot to make a forecast, then that's going to be a problem. You won't get a good forecast. The second forecasting method is something called panel consensus, which relies on having multiple experts to share information and somehow arrive at a consensus through discussions. And this method it's definitely good that to have more than one person gathering information and making a forecast, but the experts may not be equal. So for example, here's a picture of the current squad, or the 2021-2022 squad, for a very popular but lousy football team called Manchester United. I'm a Liverpool fan, in case you were wondering. So as you can see, all of these are very highly skilled and highly paid footballers. Notice who's in the middle. This person nicknamed CR7. And here he is showing off his big balls, his 5 Ballon d'Or awards. So if you pretend that these guys are experts and they are trying to decide about something, CR7 would probably have a much bigger influence on the so-called consensus because everyone admires him and he's a lot more experienced. Even when the other experts might have good ideas, they may defer to his ideas just because he is the most influential. So to mitigate this problem, another qualitative forecasting method called the Delphi method was invented. So how this method works is that they try to make a more structured version of the panel consensus method. So the experts will answer questionnaires over multiple rounds, and there'll be a facilitator who can anonymize the feedback and summarize it and pass it back to the experts, who will then revise their opinions and their predictions in the next questionnaire. So you repeat this process multiple rounds until there's some sort of consensus. So this is definitely a process that's less susceptible to manipulation by an influential expert because it's anonymous. You don't know who is saying what, and so the quality of the content or the quality of the information is more important than the quality of the person who contributes that information. Now let's turn to quantitative forecasting methods. You could actually spend multiple courses in econometrics, in machine learning, in statistics about quantitative forecasting methods. Obviously, as one topic in a lecture, we are not going to be able to cover all of that information. So what we do want, however, is just to give you a little taste, like an appetizer, of what statistical forecasting looks like. So here's a plot of demand in the last 7 years or 84 months. Let's take a look at the plot and see if the demand is random or whether you can discern any predictable patterns in this demand. So what do you think? So what you might notice is that the demand slowly is trending up. So this is what is known as a trend. A trend is usually, you can think of it as a straight line going up or a straight line going down. For some products which are perhaps becoming obsolete, the trend might be down. So trends don't always have to go up. There's also something cyclical, which means it repeats every so often. So every 12 months you get a peak, and a bit after that you get a valley. So there's a peak and a valley, peak and a valley, peak and a valley. You notice this repeating pattern, which is the seasonality. And you can basically put the seasonality around 0. It's all relative to the baseline anyway. So you can extract a repeating pattern using these quantitative methods. Then finally, after you take out the trend, you take out the seasonality, you are usually left with some random shocks where there's no real pattern, and this is truly random. Alright, so that's it. We've covered the 3 laws of forecasting, the quantitative and the qualitative forecasting methods. Let's go on to the next topic.